Right. Can someone see my first slide?
Yes, we can see your screen.
Good, good. Right. Firstly, a couple of apologies. Firstly, apologies if you saw this last year. It's going to be broadly the same with a few tweaks for 2025. So if you saw it last year, apologies for a bit of repeat. And I guess there's quite a lot of detail to get into a short space of time. So apologies if I whiz through it fairly quickly. So I'll crack on. Introduction to myself, David Philpott. I look after all the Getmapping content programs on the aerial photography side of the business. Project manager also for major projects. It's kind of leading on to slide 2. So our core competencies as a business, the main one is the aerial survey services, so capture and production, which is the bulk of what I'll be covering in this webinar. And also we are at the forefront of data hosting and streaming. So I've got a few slides on that at the end. The other strand of the business, which I'm not going to cover here, we do a lot of mobile mapping surveys as well. So that is a very active area of the business, but that's kind of out of the scope of this presentation. Very quick slide on us. So we're based in Fleet in Hampshire, southern England. We own a company called Geosense in Cape Town, and they do most of our production. And we also have flight operations based in South Africa as well. UK flight operations at the moment are based in Liverpool, which is actually very handy because it's kind of central for most areas in the country. So you can get down to the south of England and up into Scotland in equal time. So that is us. Yeah. So there's probably about 15 to 20 people in the UK, 25 to 30 in South Africa at the moment, although that goes up and down depending on the volume of production work that we've got. So the first section is going to be on how we capture the photography. So I'm going to start really by just an overview of the technology we use. So really the first slide is a little bit update, but the trends are still the same. So the trends in the technology is for larger footprints on the ground. So improved technology, improved CCDs are enabling us to have denser, more pixels in every photograph. So the upshot of that really is you can have with a larger footprints, you can fly higher for the same resolution, and it also reduces your capture time. And you can also fly with higher overlaps. I think the other thing I haven't put on there is increased cycle rates. So on the next slide, kind of an illustration of the growth, and it's grown further since I grabbed this slide. We can get even bigger footprints as well on the ground. So a footprint is the size of each the individual image on the ground, and it's improved dramatically over the last 20 years. So again,
David.
the other trend is cycle time.
Hi, David.
Sorry.
Apologies for interrupting. I have 2 people asking if you could please put the view to full slide view.
Oh, sorry.
Because they are only seeing your presenter's screen.
On this is the thing with 2 monitors. Right. That's working, isn't it?
There you go. No. Thank you.
Good. That's the thing with 2 monitors. I've got one monitor of slide presenter view and one with I had them the wrong way around. Right. Sorry, I will continue.
And feel free to turn on the camera if you want, so people can see who's talking to them. There.
Work.
Thank you.
Okay. Good. Right. Continue. I will continue. So yeah, cycle time. That is probably the biggest change in recent years. It's kind of linked to write times to hard drives and all of that technology. And the upshot is cameras can take photograph after photograph much quicker. So the latest iterations of cameras enable you to fly with very high cycle times. You can fly at faster speeds with a higher overlap. And that is a really crucial bit of technology, which is kind of a game changer, especially for high resolution photography where you need to fly low. So I think cycle time. I think yeah, there is still improvements in footprints and in the CCDs, but the biggest trend I think is in the speed of camera cycle time and write rates and things like that. All of that technology. So that's kind of all the trends. Um, and sorry, let's move on. Right, that's better. The other factor in the camera systems we've got are the variability in lens types, and the different focal lengths enables you to fly at different flying heights. And this is really important especially in the UK or any country of crowded airspace. So we've got camera systems with 100mm lens and 210mm lens. So for the 12.5cm data, the 210mm lens we can capture at 19,000 feet. It's 9,000 feet for the 100mm lens. And if you're thinking about areas in London where it's really difficult to get into the airspace. Nowadays, anything below 10,000 feet is tricky. It's a lot easier, probably above 12 and 13,000 feet. So the higher you are, the easier it is to access those hard to capture areas in busy airspace. So again, it's having a range of choices to enable you to capture the data you want. All of our cameras are the best of breed. They have red, green, blue, and near infrared lenses. So this is the bottom of one of our cameras. It's very clever technology. So it has separate color band lenses and what's called panchromatic lenses, which provide the detail. And this is all stitched together to create a super large image in processing, which actually contributes to getting you that large footprint on the ground. And again, aircraft choice is quite important. So you need to choose your aircraft depending on what altitude you're going to be flying. So if you want to fly low, you're going to need to have an aircraft that can still fly quite slow. So despite the increased cycle times, if you're flying very high resolution data and you're closer to the ground, you do need to fly slower than when you are at high altitudes. So again, depending on what you are targeting, aircraft choice is important. So, and again, the key thing is range as well. So we like to have aircraft that's got a 5-hour range, so you can get a decent time on target. You can have transits from the aircraft, get to your target site, and efficiently capture as much data as you can. So again, aircraft choice is key. These are typical examples of the aircraft we've been using this year, and there's lots of types of survey aircraft out there. So that's a bit on capture, very brief overview. Now I'm going to do a little bit on production, the production process. So again, overlap is key. You're capturing thousands and thousands of photographs of a 3D surface, and you're ultimately going to be rectifying them into a 2D map projection. The effect of overlap, one of the main things is to minimize building lean. So on the edge of your footprint, you are going to get the more effect of the lean of buildings in the photography. So the more of your image you can take from the center of your image, courtesy of overlap, the better. And again, it's always a balancing act between, obviously, the more overlap you fly with, especially side lap, which is the overlap between flight lines. The more flying you do, the more flying costs you do. So it's always trying to find that sweet spot between flying costs, efficiency of production, and the quality of the output data. But yeah, overlap is absolutely key. And then, yeah, you need to account for that, especially over city areas. We've got high buildings, over mountainous areas where you've got changes in topography. So that is one of the key things that's taken into account in flight planning. So for any block, generally we fly in east-west, north-south, or north-south lines. we are always using an 80% forward overlap. So every image is overlapped by 80% from the next. Side lap is the one that affects the amount of flying we do, and we found that really our sweet spot is now tending towards 40%. It used to be 35%. We've increased it because that little bit extra just gives you better quality data with your outputs. And again, it's just finding the balancing act between flying time and efficiency and quality of production. And again, this is an animation. This is the UK. We know what the weather is like in the UK. It's quite often cloudy. So you do need to maximize your capture windows, hence always trying to use the best available technology and hitting the right sweet spots between the amount of overlap you're capturing with and efficiency of capture and the amount you've got to do. Obviously, you do need clear skies to capture and also the correct sun angle. So we are always guided, and most main contracts are guided by RICSPEC, Royal Institute of Chartered Surveyors. So there are general standard industry guidelines that define things like sun angle, absence of shadows and things like that, which we adhere to. So again, you've got limited capture opportunities, especially in the UK, and throw in the complications of air traffic. You really do need to maximize your opportunities. We've been doing this for 25 years. We're quite experienced in knowing the weather, knowing air traffic, and planning our resources accordingly to sort of capture the data we want to capture. So that is a very quick background on capture. I'm going to do a section now on processing aerial photography to produce the products that you will see. I think the first thing to talk about is data accuracy. So again, there's a phrase that came from cycling, which is the aggregation of small marginal gains. And this is very much true in terms of accuracy. So there's lots and lots of little things you need to account for to make sure the data hits specs for accuracy. And again, as I say, you are taking thousands and thousands of individual photographs over a 3D surface in an aircraft, which is an unstable environment, merging it all together to a 2D map projection. So again, we have got onboard GPS, and we also have got what's called an IMU, an inertial measurement unit, which actually measures the orientation of the aircraft at the point of the capture of each frame. So the accuracy of both of those data sets is really key. The GPS is triangulated with the OS network of GPS base stations. So all of this stuff goes in, and it has to be accurate. All the processes have to be accurate to actually make your inputs as accurate as possible, so the output data will hit spec for accuracy. So accuracy is really key. One of the other drivers in technology, again, it's always improving, is processing the color balancing. Again, the processing algorithms are getting better and better. They have done over the last 20 years to actually, obviously, you're capturing over the course of a 2 or 3 hour survey light in different lighting conditions. And you want to get a real world looking evenly matched image. So when you mosaic all your individual photos together, they look realistic and you don't see any joins. So again, a lot of this is now taken place by algorithms. It's getting very clever. And the main thing we need to do is, yes, it's real world color, but you're not losing any information. So you're being able to see as much detail as you can in shadow areas and not having image burnout on white roofs and white objects. So again, yeah, color is key, but it's better and better all the time. And again, it can be challenging. I think London is a really good example of where it can be challenging in terms of color, mainly because the air quality is probably worse than in most other cities. So you're always operating, if you do get into the airspace, in suboptimal conditions in terms of air quality. So again, all of these algorithms that are employed are really useful in getting the best out of the data to get all the information that is there into the final product. So we're flying with huge overlap, and the increasing power of computer graphics cards enables us to use that overlap to when we're running aerial triangulation, it does thousands and thousands and thousands of calculations to find tie points across all of those individual photographs. So again, this process has changed a lot in the last 10 years with increasing computer power, and we're now able to match every photo to the pixel, where there's huge amounts of overlap. So it's a very intense computing process that is now getting quicker and quicker with added computing power. So it automatically generates tie points across all these thousands and thousands of photos, and then we also add in individually survey ground control points, which we go out and survey to 2 centimeter accuracy to really nail down the accuracy in key areas. So the upshot of this is that what the production process and the aerial triangulation process does, it can assign a 3D value to every pixel in the data set. So the upshot of that is you automatically get a DSM, you get a surface model. Now the quality or the lack of artifacts in that surface model is directly related to the overlap that you fly at. So you need that 80% forward overlap minimum to do this, and then the quality varies with how much side lap you fly at. It needs to be a minimum of 30. If you've got 60% side lap, you get an absolutely amazing DSM. Somewhere in the middle is probably the sweet spot in terms of how much is realistic to capture. So that is, an initial product. You can get it straight out of the box. You can get a raw surface model, point cloud, effectively derived from the aerial photography. This is really important in the next stage. So this slide shows the change in orthorectification method. So orthorectification is the process of flattening your data down to a 2D map projection, and it uses it used to use traditionally an external DTM to model the surface of the ground, but now that we can generate a DSM from the data, it can use the DSM to do the orthorectification on a per pixel basis. Obviously, it needs this huge computer power to be able to do that, but the results are a lot better, as we'll see in subsequent slides. So it uses all the information in every pixel because it knows the XYZ value, puts that into the calculations to orthorectify that into a 2D map projection. So you are getting it truly vertical, dependent on the quality of your input DSM, which is dependent on your flying overlap. So that's kind of a real whistle-stop tour through production. There is obviously, once we've orthorectify it, we do have to clean it up, get rid of artifacts, etc., to create the final products. So the next section is about those products. So if you remember from the previous slide on the technology, we capture in 4 bands. We produce everything in 4 bands as well. So you've got red, green, blue, and the near infrared band. So everything goes through to the production process as 4-band data. So the upshot of that is that any edits that are done on the data are done in 4 bands. So the red, green, and blue and the infrared are always synced. as you've seen, we can automatically spit out a DSM, and that can be edited to remove noise, yeah, to create DSM as a product, and then obviously then we can derive the DTM from that by removing buildings and vegetation. So there are main products. So I can go into a bit more detail onto the products. And again, if you look back to our slide on the orthorectification, so the standard ortho using the DTM, that would retain any building lean in the data. So it wouldn't account for the elevation of buildings when orthorectifying the imagery. But when you've got the true ortho, the DSM ortho, it does have that height information on all the objects, so it removes that building lean. And as you can see in the slide, that is much more useful when you're doing mapping from the data, because it's not obscuring anything vertically. As I said, we've got everything produced in 4 bands, so we can derive straight out of our 4 bands our RGB orthophotography and our color infrared orthophotography. So the color infrared takes the near infrared, the red and the green band to produce a 3-band CIR image, and they are identical temporarily all the time. So that is true for all of our data. So that is obviously really powerful. When you're doing any sort of analysis, you need all the bands to be absolutely synced. So if you're producing everything in 4 bands, that ensures that is the case. So I've got a note on here. We've got full UK coverage of everything 2021 and newer. I'll get on to coverages later. Breaking down the orthophotography data sets. So we've got 2 main products. We've got National View, which is our full UK data set, 12.5 centimeter resolution nationally. And now we've got City View, which is our 5 centimeter offering. And again, this slide, it shows the huge difference in detail you can get from 5 centimeter. And I think, again, an industry trend, a market trend, people are wanting more data at higher resolution. So I think 5 centimeter is where everyone is moving to, especially for urban areas, because it reveals so much more detail than the 12.5 centimeter data. So a bit more on City View. And again, it's really good at capturing fine features, individual roof tiles, road markings. Obviously, you can't capture the whole of the UK at the moment in 5 centimeters, so we're covering urban areas or the areas around urban areas. It is really accurate. So we are generally working with our aerial triangulation of about a 2 to 3 pixel accuracy. So 5 centimeter data, that's 10 to 15 centimeters, generally around 10 centimeters. So it's really accuracy. The accuracy is obviously reflectant on the resolution that you're capturing. So it is a really powerful data set. So this year we have been majoring on the city view capture. That's been the core of our data capture program. So we started it a couple of years ago, and we are building up our portfolio of urban areas. So the aim is to get probably up to 90 to 100, 90 to 100 biggest UK cities done. We're on about 76 at the end of this flying season. So we're well on our way to getting a pretty comprehensive 5 centimeter data set and covering a lot of urban areas. So we've done, central London, part of it, not all of it. Manchester, Glasgow, Edinburgh, Manchester. Oh, I've got that twice. So we've got some really key areas. We've done a lot of capture this year. So the green ones are what's available at the moment. The red ones are the ones that are in production. So we are working through the data we've captured this year to get that finished, available offline and available online in our web feeds. So this is our work in progress at the moment. So I've got a few examples. We've got London, we did this year. Edinburgh, which I think is round the corner from your offices. I was trying to find it in the data. So yeah, we've done Edinburgh this year, done London, which was quite a really good one to get because it's so hard to get in and capture high res data of London. We didn't get all the data for London we wanted to. We've got about 60% of it, of all the inner London boroughs, which is really good. Hopefully we'll get the next lot next year, with good luck with air traffic control. Yeah, Glasgow, Norris. So I've just got a few examples, and it just shows the detail. So there are so many applications I think we can use for this high res data. So we are building up a real portfolio of it. So we've still got the national view. So this is obviously full UK coverage, 12.5 centimetre. Everything is captured in 4 bands. So we have got the 12.5 centimetre CIR, which I think we provide for you guys. It's I think that's one of the data sets we do for you. The focus next year is going to be now to go back on to updating the national view. Obviously, we've done a real good progress in City View this year. We are going to do a lot more national view to then start updating those older areas from the national view data set. So expect to see that next year. But again, it's a seamless data set, whole UK. And again, it's still got that 2 to 3 centimeter pixel accuracy, so about 50 centimeter accuracy. Everything is captured with the same sensors, so it's all consistent across the whole UK. And again, it's it's a really powerful data set. And the other thing we've got is we've got historical photography as well. So we've been doing this for 25 years. So the first surveys was analog cameras back in 1999 we started. So we've got 25 years worth of data, which is really important for things like change detection. Since this is London, this is picked out 3 images. I could have had a slide of about 8 different images of London. Obviously, I could have added in the 25 onto that. So we've got, in a lot of areas, we've probably got anything between 4 and 8 and 9 iterations of the data that's been captured over the last 25 years. So it is a really powerful data set with all of our historic data. So moving on from the aerial photography, obviously we can derive height data. So the digital surface model. So we maintain a UK 2-meter DSM. So that is, so from the photography we capture, we can output a DSM at the capture resolution. But we are in the process of, again, it's working out what is the sweet spot for what people need for a DSM. So we've got an edited 2-meter version nationally. We are now looking at changing that to 1 meter. But we've also got the raw unedited DSM that comes out of the production process. So we've got 90% of the country covered by 25 centimeter DSM, really high resolution data. And we've also got 5 centimeter DSM for the cities. So again, it's a very big data set, but again, there's quite a lot of potential there, which we're kind of starting to explore with customers to see whether this is going to be useful to them in their products and services. We're looking, talking to people like solar companies, because you've got really good information on the orientation and angle and areas of roofs and things like that. So there is a lot of potential in high resolution DSM data, which we're probably only just starting to unlock. That is kind of a work in progress of what can we do with this data? How can we productize it? How can we get it out there? Because one thing, it's really high resolution, but it's really big data. So a 1K tile of 5 centimeter DSM is about a 1.5 gig. So it's a huge amount of data. So it's kind of balancing up. Again, it's hitting a sweet spot between the size of data and the detail of data and what people are going to want it for. So again, that is a journey we're on with the DSM is to work out, well, what is people are going to be wanting, what's going to be useful in terms of resolution and data size. So we've got a lot of offerings in that space as well. And then quickly, obviously, then if you've got a DSM, you can edit out and create a DTM. Again, we've got 4K UK coverage at 5 meter. We are starting to update it at 2 meter resolution. Now, again, it's a conversation with customers, the marketplace is what is the sweet spot that people require from a DTM in terms of resolution. I don't think there's any point in serving up a 25 centimeter DTM and you're not going to gain too much in detail for what most people need. So again, we are looking at increased resolutions for DTM, but again, it's a conversation with users to see what works for them. But again, storage, computing technology, processing speed, it enables you to produce data at higher resolutions quicker. So all of this higher resolution data is possible from a production point of view. And is just finding, or what are people wanting to do with it, and what is the sweet spot in terms of resolution. Final one on is where we're looking at in the future, and again, it's derived products. So we've got all this data, dense data, detailed data. What can we do with it? And again, one of the big things in the industry is the use of AI to extract information from that data. So we are looking at using AI to extract vector data sets from all of our aerial photography layers. So things like building models, vegetation models, land use classification, and obviously you can derive contours. So again, these are all things that are in development, looking at the capability of using AI and what can we get out of it in a conversation with customers as to what sort of data sets they need for all of their work. Finally, I've just got a few slides on managed data services. Again, this is a really important strand to what we do. So we were at the forefront of pioneering web mapping services. We did it when internet bandwidths were tiny. So we've actually developed in-house bespoke data types that are really efficient at low bandwidth. So now in an era of high bandwidths, our web services are really, really efficient when being hit by lots and lots of users. So we serve out the data, all of our data layers in WMS, WMTS, web feature services, and we're looking now at web content services, especially for height data as well. Those big height data sets, what can we do to stream those out with a web content service? So again, this is a really powerful way of getting the data to the users, and they don't have to worry about updates. So we do the updates for them, and it's probably the way people should be consuming data these days. I think that's it. That is my last slide. So really quick. I hope that wasn't too whistle stop and gives you a sense of what we do. And hopefully you can see some of those products in what you use in Digimap. And thank you, and open to any questions.
So when you open Digimap, that's what you're going to see. And depending on what service or what collections or packages you have, they will all appear here on the top. And you will click, for example, on Aerial. And you have Aerial Digimap and Web Services. Web Services is where you can get a link to add the Aerial collection to other collections. And the Aerial Digimap is where you can see all the maps that David was mentioning before. So I will start from the very bottom here, or where you have the download map. And the download map is where you can find most of the maps that were mentioned there. So the city view, high resolution 12.5. So I can download the map. So you can see, I will just zoom in anywhere in the map, and you can see from the base maps, as you zoom in and out, it is going to get blue. And I zoom in a little longer, a little more. Yeah, now it is blue, and I can click and choose what type of map do I want, what type of base map, and it will depend a lot on how much zoomed in you are. There will appear more. So now I have the 50 centimeters and the 25 centimeters, and it will keep on showing more, the 12.5 centimeters. So I can see those maps just by browsing, just by looking at my map, and I can also download those maps. So to download a map or to print a map, I can go up here and click on print. I will print what is on the screen. If I want to download my map to add to a GIS file, for example, I will click on the map. I will click on the availability grid, and everything that shows purple is available to be downloaded. So next step is to get the piece of map that I want. And I can either have a rectangle or a free polygon, a buffer, or I can use coordinates, tile names, and select the visible area or import a polygon from elsewhere. So I will just click on the rectangle here, click at the beginning, go away with my map, click at the end, and I can look here. If those numbers did not turn red, it means I can download this piece of map I want, and I will just add to basket. And here I can select the format sometimes, and sometimes it's just what is given to me, and then request download. As you request download, you'll receive an email with the download, and you can have your map as well. When you first enter to your area of view map, I will leave this and clear. You will see the license agreements. So you will have to accept each one of the uh, collections. I've accepted them all, so they are not in red, and I don't need to do any action here. But to see the collection, you will have to open and accept the license.